Welcome to First the Future, where we explore the past, present, and future of digital engineering and PLM. In this episode, about engineering simulation, three of our own experts, Slav from TECHNIA Poland, Ben from TECHNIA Canada, and Graeme from TECHNIA UK, share their thoughts and discussions about how simulation has evolved from its academic beginnings to the powerful and AI-driven technology that is shaping design and innovation today. They discuss the changing role of simulation across industries, the growing integration between simulation, CAD, and PLM platforms, and how AI and machine learning can redefine optimization and trust in digital models. They also explore what the future might hold, from digital twins to quantum computing. But without further ado, let's dive in.
I guess we start with a kind of round table, don't we?
Yes, my name is Slav. I've got background in mechanical engineering and computer science. So the first time I actually tried FEA, it was during my bachelor's at mechanical engineering. And it was the time when I did a simulation of skateboard. So it was a long time ago. Then during my master's, I did an excellent simulation of a spur gear. And that's where I had to learn a bit of Python as well to speed up the entire process of simulation. Yeah, and since 2015, I've been working in TECHNIA and doing Abacus support and consulting as well. Yeah, that's pretty much me.
Wow, so you hit the 10 years mark recently.
Yes, exactly.
Congrats.
4th of November.
Go on, Ben, tell me about you. I'm interested in this one because I don't know a lot about your background anyway. So come on, give me the whole history.
Sure. Well, it's not going to be super innovative. It's also a mechanical engineering background. I did an aerospace engineering degree from France, university called IPSA. Then I moved to Quebec City in 2012 to do a master degree in mechanical engineering on composite material. And this is when I was introduced to the one and only Abacus CAE. And at the beginning, I didn't really like it. It was not super intuitive. It was a bit cumbersome to work with. And my research thesis was trying to characterize the delamination of woven composite material. So I had to do some experiment in the lab for delamination and some FEA to reproduce that and play with the evolution factors and just replicate. Yeah, so I graduated in 2015, and then I started working with Mathieu at Optimec, and the research was, do I want to do design and conception? Do I want to do analysis? And then I met someone who was working with Astran, and he said, like, he convinced me, like his passion convinced me about, you're going to learn so much about the assembly you're going to work on. You're going to learn so much more than just by design, because you're going to see that thing deforming. So anyway, he transferred the passion and been doing that since 2016. So nearly 10 years mark as well, Slav. I'm going to catch you.
We need to talk because I first met Abacus 97-ish, something like that, when I was doing a first degree. We were kind of teaching, or we were being taught kind of numerical methods in Bristol. I'd kind of fallen into doing an engineering degree because I was kind of interested in how things work, but I didn't really know that was engineering. I've got a scar on my head from when I was about 6, when I saw my dad kind of grinding valves into a cylinder head. And when he went to get a cup of tea, I tried to do it myself, and I had to get up on the chair to do it. And I fell off the chair, and I've got a scar from doing it. So for me, it's always been about understanding how things work. So kind of simulation is perfect for that. You know, with a spanner, you can understand what it feels like to do up a nut and when things start to yield and stuff like that. But with simulation, you can follow that entire process through in kind of multi-dimensions and see everything that's happening all the way through. But yeah, I kind of fell out at the end of the degree. Didn't know what I wanted to do. One of my lecturers at the time said, "Oh, one of my PhD students has fallen through. Do you want to come and do a PhD?" And I went, "Sure, that sounds like fun." And that was in Bristol at the time. The A380 was being developed and things like that. So I was also doing modelling of delamination, but also from a residual strength perspective on kind of curved panels on the leading edge of the wing, and kind of fell out at the end of that. And that was pretty fun. So I met Abacus there. Kind of thought I was a god, kind of solving these 800 element models with dual-sided contact and all kinds of crazy stuff going on. But yeah, we'll come back to that. And it kind of fell out at the end of that. And a guy that kind of graduated from the PhD group a year before me just randomly phoned up one day just as I was finishing and said, "Hey, I'm working at this consultancy. Do you want a job?" And I went, "Yeah, okay, let's do that as well," without really kind of thinking about it. And kind of 15 years later, I'd still been playing with Abacus, and then that kind of fell apart in the kind of economic crash. So that company got bought out, which is where I met Slav. with our time at SSA. So we kind of swashbuckled around the country doing fantastic work for about 3 or 4 years there. And then, then we got bought out and became part of the TECHNIA team for, like you say, Slav, another 6 years. So yeah, I've known Abacus for getting on for 30 years now. And it's around our house, it's a bit of a joke that I've known Abacus longer than I've known my wife. And she doesn't really like that. But here we are, we're very loyal engineers.
Wow, that's impressive. How exciting must it have been to start working on the A380 at the early days?
It was kind of ironic because it was, we kind of told Airbus what we were doing and they said, oh, that's quite interesting, but, we're not really interested in picking it up as a kind of Airbus project. And then when it got to the end of the PhD and we kind of went back and showed them results, they said, oh, that's really interesting. Can we have the results now? It's like, it's too late, guys. It's in the public domain. You should have put your money up at the start. But yeah, it was pretty cool living in Bristol and seeing that project develop and then kind of seeing the planes in the sky kind of flying around and yeah, it's cool stuff. But kind of thinking about back to that time, when we were starting out, what was simulation like then back in those dark days when everything was in black and white and, it was a completely different landscape perspective, but I'm interested in yours. So.
It's one thing that I'm amazed about is I feel like today we still have work to do to educate people about the power of simulation, about what it's capable of, that you can trust the result, that is just a mathematical model behind, just not random colors if you use it right. So I don't imagine how it must have been 10, 15 years ago. That work comes from a long slope, right?
Yeah, it was, you're right. Kind of back then, it was a bit weird and wacky and it was still kind of in the realms of research. And it's like, oh, nobody does simulation out in industry. This is this is what academics do and things like that. So I think you're right. I think it's gone in kind of steps. There's adoption in certain industries and not in others, and then another industry will accept it or whatever. But it's still quite interesting that we still meet customers who do no simulation whatsoever. It's kind of, well, we always did it like this and it doesn't break. And you kind of go, well, that's fine, but you're leaving so much performance on the table potentially, not just absolute performance in the part, but are you just wasting material? Could you make the same product with less material for the same performance and save yourself some money? That's the business efficiency, which I don't think a lot of people see. But I guess you see the same thing, Slav. It's kind of...
From time to time, I speak with people, and if someone doesn't know anything about engineering, CAD is the term that they usually can understand, but it's the last thing they can they know about. So yeah, FEA, CFD, they often use the CFD term for financial stuff and not for engineering, which is also quite interesting. Yeah, but things definitely change. I remember when I did the skateboard stuff, it wasn't Abacus, it was ANSYS, but it was the very first version with black and white thing. And yeah, it was it looked like very first version of OpenGL. And it was the case that I literally built the model from scratch by creating the points and creating the edges manually. And nowadays it's just, it's a lot faster. The technology moved significantly further.
I also feel like the industry leading the technology for finite element analysis has changed. I feel like initially aerospace industry was leading the edge because they needed to go lighter with newer materials. So they needed to reduce the safety factors by having more. But I feel like now the most innovative simulation that I see doesn't come from the aerospace industry. It comes from high tech, from life science.
Yeah.
Did you felt that switch also? That switch?
It kind of falls into two camps, I think. Once you've made that switch with people to kind of go, okay, this is what simulation can do, their kind of ideas run away. Then they kind of go, oh, well, that was amazing, but can we do this and can we do that and things like that? So we often find that kind of the projects fall into two levels. It's kind of big lumps of steel and people just want to check that you're not at 80% yield and things like that. And they want it done at minimum cost and blah, 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 blah. But it's still the input of the engineer kind of at the end of it. It's often kind of going, well, your design passes, and they go, okay, that's what we asked you to do. And then you can kind of say, but hang on a minute, as a result of doing this work, I can see that, this beam is doing no work. You could lose that from your design. And this beam is doing a lot of work. So you might think about adding a bit of extra material there, which might mean you could lightweight elsewhere. So there is still absolutely a place for the simulation engineer, for the guy that kind of builds the models, understands the approximations that they're putting in, and therefore can do the kind of uncertainty qualification and the results kind of live in their head as they're going, and actually bring those results to life at the end of it. We all know that a static report, just contour plots in a report, is not super helpful. It kind of records what was done as kind of evidence that was there, but that's often not where the real magic happens in terms of the engineering value that simulation can bring. So there's still, okay, we're dragging people towards this technology and the value that it can bring technically and from a business perspective. But once you've kind of lit that blue touch paper on the process, you find people kind of talking about multi-physics 5 minutes after you've just shown them the linear elastic solution. It's like, oh, hang on, guys. Okay, we're orders of magnitude difficult there.
Yeah. I think the requirements towards product changed significantly. So I assume that when FEA started, historically, it was like more aerospace, more like space industry, that kind of place. But now it's more toward, I don't know, as you said, high tech or healthcare or some like daily use products. And to be competitive at the market, you need to use the right tools, the latest technology. So I think that's where we actually see more from this kind of not exactly engineering industries, some kind of simulations that people want to perform in order to find the best kind of design for some daily use products.
Yeah, I've never thought about getting into some of the projects I had the chance to work on, but recently, just two funny stories. We came in contact with a customer that was developing like decorative wall for the cities. So their design was upon a plastic clip that you just clip on the stone wall, and then you hang your decorative whatever on top of that. And they needed to do FEA for that because the least amount of plastic you can optimize made huge difference. The type of manufacturing with the tolerances make a huge difference, and the time for which this weight has to hang, you start to model creep and aging of plastic, and it becomes this like PhD project that you can lead towards just for decorative wall. And the other one I can think of is the fishing industry. We had this company from the East Province of Canada comes, and they wanted to develop a smart buoy, like a smart fishing net that was able to adjust the depth of the net, so you're not sure not to drag the bottom of the sea and catch just the right species of fish you're aiming for. And this buoy was made of plastic extrusion and had to sustain crazy amount of pressure, and they wanted again to optimize the design. So you're right, Slav, like FEA now are everywhere.
But I think that's our responsibility, isn't it? It's to take our experience of using these tools and kind of see these weird and wacky ideas and go, it's just physics. I have a physics engine which can solve that. So if you've got the time to talk to me about that and you've got a bit of budget, we'll work with anybody to try and use these tools to make any product better. And that's really cool. And I think, we're, as we've said, we're mechanical engineering geeks talking about mechanical engineering things here. But the scope of the way simulation is used now, kind of discrete event modeling for kind of modeling handling processes and what is the optimal way of moving product around environments and things like that. That's all going to feed into the future where it's not just about analyzing components or assemblies, but how does that assembly work in an environment throughout its life cycle. So it's kind of, I don't know, for me, it kind of feels kind of weird that we've kind of got to this point where component and assembly level mechanical simulations are just on the cusp of being accepted by everybody, but the technology is moving things along already because we can now manage bigger data sets and we can build bigger models and we can look upstream and downstream in the product life cycle. You're right, Slav, when people talk about CAE, they used to think just about CAD, but I think that's shifting to think further downstream in terms of the whole engineering cycle of the product, which is really exciting, but really scary at the same time. So, it's kind of, where is the future of all this going? How does it feed into the wider PLM journey of any product as well? And kind of what does that look like going forwards? I guess then your kind of further along the road of adopting 3D Experience platform for doing that. So, what's your expectation of where this is going next?
Yeah, it's a very good question. And it's again a matter of education. And you're right, the technology moves sometimes we feel faster than companies' culture, engineering companies' culture. And the biggest switch I've seen with the 3D Experience platform is the fact that you have the simulation integrated with the CAD inside a unified environment that only allow for new workflow to develop your product way faster. And sometimes we have this buzzword, we call it design driven by simulation. So now instead of the conception phase, the designer already try to hand calc and size the thickness of their steel part or sheet plates upon a load case that comes from whatever, and then build the first prototype and go to test it, and then run FEA, optimize the prototype. Now you can just create the CAD with parameters. So just by changing a number, you update your CAD and you run simulation to help you size your design. Yeah. So you run FEA earlier stages of concept. So the FEA analysis and not the designer, the FEA analyst will tell you the size of your design. Yeah. And that leads to tremendous reduction in conception phase because you already have a design that meets the requirement if you start by the right approach.
Yes, and you kind of build in that digital thread, don't you? Everything is documented. It's not just some weirdo's idea on a Friday night or whatever. It's data-driven. There is that digital thread. It's interesting though, Slav, you in a room of three weirdos, you're the weirdest of a lot of us, I think, in the sense that, you're playing with the kind of visual scripting and using the CAD parameters that Ben's talking about, but also kind of starting earlier with the 1D simulation using Dimler to kind of explore the physics before you ever get to kind of 3D parts and assemblies.
It feels like we are at the edge of some disruption in the sense that some people started talking to each other and it's like the work can be combined within a single environment. Mm-hmm. So like talking about 1D solutions, it feels like systems engineers can now do collaboration work with proper simulation engineers. I don't know.
Simulation engineers. So.
Okay. FE engineers, let's put it this way, or CAD engineers. Don't try to offend anyone. My point is that I think in the past it wasn't exactly working that well. As you mentioned, like the hardware is better now. So we can actually run a coupling, run some kind of multi-physics simulation and do it quite quickly. In terms of the geometry, and the visual scripting, the reason why I think we are like getting some new technology, it feels like with the visual scripting, you can generate some fairly automatic workflows that can generate data exactly for simulation. So previously it was only like possible with Python scripting or some kind of workflows like that. While in the visual scripting, you can link the blocks together to create parametric models. And then those parametric models can be quite sophisticated. Like it doesn't have to be only, let's say, a height or width. It can be the total area of the object or the mass or something like this. And so it feels like this environment creates the backbone for any optimization process, for any AI training or anything like this. It's all well packaged. It kind of, there is everything within the tool set that will let you create this parametric model that is very easy to actually redesign. So you can put different parameters and it will help you create if-else statements, if that makes sense, to kind of create the conditions to make it really reliable.
So that's kind of where we are, or where we're on the cusp of. So it kind of neatly leads towards what's the future? What don't we have that we would want? And Slav, you said the two letters which we haven't said for the first 15 minutes, which is AI already. So what do we need? What is AI potentially going to give us and not give us? And what's even beyond that? Let's look into the crystal ball and see where all this is going. So AI, Ben, what do you think?
Yeah, AI. I see two ways that AI can come and transform simulation. The first one is the most obvious one, is the machine learning. So once you run a design of experiments, so you run 20 to 200 iteration of the same design, but with variation, and you then use statistical approach to make engineering decision, Well, running these 200 sets takes tremendous amount of computation time and power. The idea with the machine learning algorithm that is under development, from what I've seen, is that instead of running the full scope of the 200 one, you will train your algorithm. You will just run maybe 12, 15, 20, depending on the type of physics. Could be a fully crash of a plastic bottle, can be just a simple static load, could be CFD analysis. So you run enough, so you train your algorithm, and then the next iteration is going to be predicted in milliseconds. No more hours of compute power, but just milliseconds. But that's true if you stay in the scope of the assembly that you initially simulated. If you change too much the stiffness, or you add another part, or you change it too much, you have to retrain your algorithm. But it's able to remember the first training, so you just need maybe 5, 6 iterations to retrain it. So that's the machine learning aspect of AI that I can see. And that's going to be super useful and valid for companies that do a lot of variations of design. For smaller company, not that may be useful.
But do you think that, we have parametric design exploration tools and kind of gradient optimizers already? Do you think that's still an appropriate tool where you're looking to optimize a one-off design where maybe you don't have to explore the whole design space? You just want that one solution for a particular problem?
Yeah, absolutely. That the technology that is here already, this parametric design optimization, is already like the most underrated tool on the 3D Experience platform. It's amazing what it can do, what you can learn from. We talked about learning from FEA. That's the ultimate tool. So machine learning is just the next step from that. That maybe not everybody will need to go there, but for sure it's going to be amazing for some people. For some other, the tools that exist already are already there. And the second AI, but I'd like to hear your over it, is the AI agent.
Yes.
That could help you for model building. And Slav, as you script a lot, maybe you have a better view of that. It can come.
Well, I guess that's what you're alluding to, Slav, isn't it? It's like the tools are all there. They're in, they're under the bonnet waiting to go for this kind of brave new world.
Yeah, so I actually would like to refer first to the optimization and like this kind of deep learning process as well. So I think there is still like some technology to be developed, and I read recently about some new deep learning techniques, and I think they are somehow related to both geometry and like simulation techniques. And I think what is interesting in them is that, let's say you've got a model and it's a CAD geometry and it's made of like some dimensions. Let's say you've got 10 dimensions, and you can train a neural network, which is based on either mesh or just typical CAD. And you can minimize the number of dimensions so that it will recreate, for example, from 10 dimensions, you will have only 3 variables that will drive the entire design space, which I think it's crucial. If we want to optimize anything, we want to minimize the number of variables that we use for the optimization, because that will speed up the process. But what also happens during this kind of minimization of variables numbers, the latent space is created, and the latent space is quite good for optimization because it's smooth and continuous. Unlike if we have a CAD geometry, which we play with the dimensions, the design space doesn't have to be continuous. So from this perspective, the deep learning and AI process might be very good because it kind of opens a new space for exploration. And obviously it won't be applicable for all sorts of stuff. But let's say you've got a model that computes for 15 hours and you would like to run number of iterations of it because you would like to optimize it. In this kind of scenario, the training, I did some research, and the training typically is around, 20 hours on like huge hardware. But in any case, it feels like it's very similar to running a typical study. So if you run, as Ben said, 15 number of iterations, 15 number of simulation, and then you train the model on those 15 runs, then with the machine learning model, you can optimize the design space very quickly. So from this perspective, it's actually valuable to run the deep learning process and understand the entire design space. And I think what also happens in here, and what is probably missing very often, is that it will kind of create a compounding effect. So if there is a company that produces something every year and they change the design space every year, they can run a set of simulations that they can train the model once per year. And then the next year they will change the design. They will just retrain it. And they can also check what happens, how the design change from the previous iteration to the current iteration, and how that affects like mass distribution, stresses, etc. So I think through the time, if there is a neural network created for each application, I think it will only increase in value in the sense that it will gather the entire knowledge from the company about the design of product, etc.
So you see one unique neural network per product, per project, per company.
Per application, actually. So it can be even the case that you've got a neural network for CFD simulation and for FEA. And then you retrain them every year. And that's how you gather the knowledge from like different sources and you increase the knowledge through the time.
See, this was really interesting because we started right at the beginning. It's like, how do you trust traditional FEA models, even our simple models when we were young things doing clever things? The trust issue is still there. How do we trust a machine learning model to give us a true representation of the physics? How do we convince regulators that our neural network model is accurate? How do we apply BVUQ procedures to our machine learning model to make sure that we're not under-predicting or over-predicting and missing things and things like that? To ultimately, I guess, where we're going with this is to true digital twins and virtual twins of systems and things like that. We have to be able to believe our models. So everything is different, but nothing's changed. It's
a very good point. So like today we are running 2-3 different simulations just to replicate an experimental lab test to gain the confidence in FEA. So will we have to do the same to run 3-4 full analysis to make sure that the data generated by the machine learning algorithm is accurate?
Do we need more procedures as to how we do machine learning properly? So we will train on a data set, but we will keep some data back in order that we can put that into a full physics model and see if the machine learning model would spit out the result that a physics model would predict to validate our models. Yeah, I still think this needs thinking about, but in examples where we might be going towards really, really complicated multi-physics digital twins, where we cannot do the experimentation first. I'm thinking of kind of nuclear reactors or space vehicles and things like that. The first time we find out whether this thing works or not is when we turn it on for the first time. We need to have some pretty robust rules around how we test and validate our machine learning models, because they are going to, again, we come back to the idea that digital twins are going to provide not just technical benefits, but they will need to provide business benefits as well. If they are not robust in both senses, then suddenly we're sitting on top of a technology bubble. Because the one thing about machine learning technology is, yes, we can make our training spaces very dense so that our machine learning models are very accurate all the way across the response surface. But how many models did we have to run? What is the environmental cost of doing that? Where's the we might have built a better product first time, so we've used less material, but have we burnt a load of resources up front? So we're just robbing Peter to pay Paul in order to make that better product. So I like the idea of neural networks, Slav, as a kind of even a next step already, even though we're not there with machine learning models and trust yet, but thinking about ways that we build sustainability into those processes to try and get the best bang for buck in the entire product life cycle, not just in particular regions of it.
One thing that is actually worth mentioning in here is that at the moment, the deep learning techniques in engineering will be slightly different comparing to LLMs that we, let's say, use. Because if we ask the chat, it will generate some text and it's up to us to check whether it's valid or not.
Yes.
And with the deep learning techniques, there are actually some error measuring techniques. So let's say you've got the training data and you've got the new model generated by machine learning. And there are some ways to quantify what is actually the error and how much it guesses. So that would be one indicator to show, like, are we far from reality or not? Or are we far from the training data and how much we can accept, like how far we are? And we are talking about multidimensional space as well, not only like simple cases. At the end of the day, if we want to optimize the product, we'll run a machine learning model. We'll generate the design space in which we can actually optimize it fairly quickly because it's smooth and continuous. And then we can, when we find some kind of solution, we can always rerun the model and figure out what is the response it gives us. Is it actually matching or is it not? Yeah. If it's not matching, then we can retrain the entire deep learning model based on that. So I think that's, as a step forward, I think it's even valuable to create this kind of design space approximation because very often it's like finding the right equations is more important than like getting the equations right. So yeah, approximation is still a valuable result, I think.
There's going to be spaces for AI. I think the best use case for AI in simulation are the cases that we haven't even thought about yet. So, AI for guided workflows through the entire process, being able to take the grunt work out. It's still a button clicking exercise doing a lot of simulation models. So anything where we can build help into that process to speed up the model build process is going to add value. But, being able to search documentation contextually and get better answers faster, I think that's going to be, because you're right, Slav, it's a lot of the best uses of AI at the moment are kind of context insensitive. You can interpret the output in any way that you want to, whereas physics is a bit more precise if you're going to use it as a kind of a brute force tool. But even using AI to be able to help interpret the results downstream as well, to be able to interrogate data sets and give us summaries of what the meanings of these data sets are, that will be quite useful as well.
Yeah, especially when the data comes from experiment. So we can run a simulation, we can train the deep learning, and we can actually use the experimental data as a validation tool. And it will tell us how much not only our deep learning model is from that data, but also probably like simulation, which I think it's quite powerful method to use. Might solve quite a lot of problems. And the fact that it actually like works not only on CAD data or simulation data, but also on meshes. I can imagine like performing a 3D scan and some AI method to extract the geometry. And let's say we've got impact tests from two brains, and we can actually, if we train deep learning methods based on a few training points, we can actually morph the data and find out for different human how it would look like. And this will be, I think it will be hard to do it manually. Even creating the entire model, FEA model, will be hard because it will consume quite a lot of time to mesh and everything.
Yes.
While in this case, the machine learning method is probably like a black box solution, but it might be good enough to figure out quickly what's happening.
Yes, that's okay, because your data set, when you're dealing with humanity, is so large that you need an approximation at some level. You can't hope to do full physics every time, because that's just going to consume the universe in terms of compute. Is that kind of where our crystal ball ends at the moment then? We're on the cusp of that next technological revolution. Do you want to look even deeper into the future and say, well, okay, let's say we've cracked all these problems and AI is allowing us to contextualize these huge data sets? Are we looking forward to quantum computing or things like that in order to allow us to run even bigger data sets even faster, so that we're kind of near real time at full physics? Is that, or are we're just inventing the future at this point? There's no point speculating.
Yeah, I think it goes so fast that probably in 2 years from now, we're going to be talking to agents helping us building finite element model and writing the report already. So to guesstimate what's going to be happening in 10 years with quantum computing is sci-fi. It's another exercise. I would like to do it, but it's going to be speculation. If we trust the indicator of trust that the deep learning algorithm will tell us, that's not going to be a high grade.
Well, I think that's probably a good point to finish on. Let's all come back again in 10 years' time and see if we were right or wrong.
Sounds like a good idea.
Thanks, everybody.
Great. Thank you very much.
Thank you very much.
That was First to Future, the TECHNIA podcast series and our episode on engineering simulation. A big thank you to Graeme, Slawomir, and Benjamin from TECHNIA Simulation for sharing their expertise and perspective on the evolving world of engineering simulation. To learn more about how TECHNIA helps businesses innovate through advanced simulation, design, and product development, please visit technia.com or follow us on LinkedIn to stay tuned for our posts. Thank you for listening, and until next time, keep exploring, innovating, and engineering the future.